All right, first one. Actually, let's do this randomly. Oh, first one I'll just call on somebody. Cal. Cal, what'd you get for the first one? T? How'd you get that? Which law did you use? You sure? What's the other one, Cal? Somebody help him out. What's the other one? Amani? The law of detachment, yes. So remember, the law of detachment we're going to use when we have a conditional, which the first sentence is a conditional, and we have a statement. And the reason it's called the law of detachment, this might help you out a little bit here. The reason it's called the law of detachment is because we're detaching the conclusion from the hypothesis. So we're saying that whenever the hypothesis is true, then the conclusion is true. And then we have two separate statements. One statement that says that the hypothesis is true, so then we can detach the conclusion and say that the conclusion is true, and we have that by itself. Does that kind of make sense? Okay. And not only did we use the law of detachment, but which form did we use? There's two of them. One of them's confirm the hypothesis, the other one's negate the conclusion. Anybody? Chris? Confirm the hypothesis. So our statement says that the hypothesis is true, so then we can conclude that the conclusion is true. All right. Devin, how about the second one?
NBC.
Okay. You guys agree with her?
No.
Uh-oh. You sure?
Yeah.
Uh-oh. All right, let's try somebody else then. Steven, what'd you get for the second one? Not R. Do you guys agree with him?
Yeah.
Ooh, okay. Steven, I think we know that we're going to use, if we can make a conclusion, we're going to use the law of detachment for all these, right? So we use the law of detachment, but did we confirm the hypothesis or negate the conclusion?
We negated the conclusion.
Exactly. So this statement here, not T, says that the conclusion is false, so that we can conclude then that the hypothesis was false. Does that make sense, Devin? Okay. How about the next one, Caitlin?
NBC.
Okay, and why is that no valid conclusion?
Because you cannot confirm a hypothesis nor negate the conclusion.
Okay, good. We can neither confirm the hypothesis nor negate the conclusion. In fact, this confirms the conclusion here, which is one of those things that doesn't work. Did we use the law of detachment on this one? No. Why not? We didn't use anything because we can't use the law of detachment. We can't make a conclusion. So anytime there's no conclusion, we're not using one of those laws. All right, how about the next one? Cal, I got you again. I'll skip over you, though. Trey.
Next one is W.
Do you guys agree with him? Cheney, what'd you get? Chris Deeker, what'd you get? Not W? Do you guys agree with that?
Yes.
Okay, why is it not W, Chris? Okay, so this T here does negate the conclusion. That T negates this conclusion, which means that the hypothesis is false. Remember, if we negate the conclusion, we're essentially using the contrapositive, and the contrapositive would look like this. So we would conclude then that not W is true. Does that make sense, Trey? Okay. And the last one, Hannah? Okay, do you guys agree with that? Yeah. This one negates the hypothesis. It's the opposite of the hypothesis, so you can't do anything with it. Any questions on those 5? So we used the law of detachment 3 times, the ones where we make conclusions. We tried to use the law of detachment the other 2 times, but it didn't work, so we get no valid conclusion, and we didn't use one of those laws. Okay? We good with the law of detachment stuff? All right, so moving on then to the law of syllogism. First, we are going to have Chris Cruz.
I got if R then D.
If R, then D. You guys agree with him?
Yes.
Which law are we using there, Chris?
Syllogism.
The law of syllogism. In fact, all of these, if we're able to make a conclusion, will be the law of syllogism because there's 2 conditionals. Exactly. Since there's 2 conditionals, then that's when we're going to use the law of syllogism. How about the second one? Monte. If S then R. You guys agree with that? So do you agree with it, Logan, or you just put it down for fun?
I agree.
I don't. Let's see if somebody can explain why. Carly, can you tell me why? No? Okay. Bailey? No? Alright, Emma? No? Oh man. You guys remember what a contrapositive is? Let's do this one together. Please don't tell me no. We need to know what contrapositives are. They're like really, really important. The contrapositive of if P then Q is what? That's the converse. If not Q, then not P. And we know that these two mean the same as each other. So here, since we have an F and a not F, since they're the same letter but they're not the same, we're going to use the contrapositive to make them the same. It doesn't matter which one we change. Do you want to change the top one or the bottom one? Top? All right, Logan. So what is the contrapositive of if S then not F?
If not S, then F.
Amani, help him out.
Okay, I mean,
Just tell me what the contrapositive of the top one is.
okay, if F then not S.
If F, then not S. Remember, you have to flip it and negate it, right, Logan? Yeah. Okay, that's what he meant to say. Now, looking at these two right here, can we make a conclusion? Why not, Amani?
Because F is a I forgot the word for it. It's not the conclusion.
It's the, what is it? The hypothesis, right? So F is the hypothesis in both, and when that happens, we can't make a conclusion. Okay? The only time we can use a law of detachment is if the conclusion of one matches up with the hypothesis of the other, like we had in this first one here. Conclusion is T, hypothesis is T. When the first letters match up, it's not going to do you any good. You can't make a conclusion. Okay, so we are going to say NVC. Okay, next one. Will.
NBC.
Why? You're going to have to be able to give me a reason. Because I just said that the conclusion and the hypothesis have to match, and that didn't happen here?
I don't see it matching.
Okay, that's true. The Z doesn't go with the T, and the Y doesn't go with the not Z. But we do have a Z and a not Z here, right? So what if we made this not Z into a positive Z? Could we do that somehow?
Yeah,
Like kind of what we did down here?
maybe.
Maybe? Using the, what's this called? The contrapositive. What did you say first? What did you say?
I was gonna say the Matilda.
Okay. Yeah, let's use the contrapositive. Can you tell me what the contrapositive of this one here would be? First of all, does anybody know why I'm using this one instead of this one? Jamie? Yeah. I'm using this one here because I'm actually not going to get rid of any knots, but I don't want to have more knots in here than I have to. And if I use this one, then I'm going to end up with 3 of them. I'm going to have 2 here and 1 here. So by doing this one, I'll get rid of the knot on the Z and put a knot on the T. So what's that going to be, Will?
If not,
Nope.
no. If Z, then not T.
Perfect.
That's what I meant to say.
If Z, then not T. Good. And now, Will, looking at these two, does it look like we can use the law of syllogism now?
Yeah. Yes.
Well, you sounded a lot like Logan there for a second. Yeah, we can, right? And what would the conclusion be? Where are we going to start? Should we start at not T or should we start at Y?
Shannon was trying to distract me. What did you say?
Should we start at not t or should we start at y?
Why?
Which direction are we going? We're going to start at y, right?
Yeah.
Because we're going to go that way. Because the arrow's going to the right. So we'll start at y. So we'll say if y, then not t. Now, had you done this a different way, had you done the contrapositive of this one and said if not z, then not y, then what would your answer be? If t, then not y. And do these two mean the same thing? Yeah, they do. So either one of these would be okay here. Okay, good job, Will.
Thanks.
Jamie, you get the next one. Can we make a conclusion there? Yes, we can. What are we going to have to do first? Okay, which one do you want to do? Okay, what would the contrapositive of that be? If not z, then w. Okay. And so you said now we're going to be able to use the law of syllogism because we have that? Okay, and what's the conclusion going to be? If not z, then not t. Okay? Somebody else, real quick. If you had done the contrapositive of this one, what would your conclusion be here? Amani? If t, then z. Okay, both of those are perfectly acceptable. Either one would be okay. All right, and we've got one more here. Shannon. Okay, do you guys agree with her? Okay, how could we show that, Shannon, just to make sure, what can I do with one of these to make sure that we're not going to be able to get a conclusion? Okay, which one do you want to do?
The first one.
Okay, what would be the contrapositive of not j, then h?
If not h, then j.
Okay, and so looking at these two, why do we not get a valid conclusion?
Because the j's are on the same side.
Exactly, the j's are on the same side. They're both conclusions in this case. So earlier when we had a no valid conclusion, it was because the hypotheses were the same. This time we get a no valid conclusion because the conclusions are the same. Yay. Any questions about this?
No.
You guys feeling better about these?
Yep.
Yeah? I want you to get this worksheet out. So I would like you to just look this over real quickly. Look at the conclusions that I've made and see if you agree with them. And if you don't, try to figure out where you went wrong. I will be looking at this worksheet fairly closely when I check your binders next. I know I told you I was going to do that this week. It'll probably be next week. But I will be looking at this closely and making sure that you're doing all of those things. So if you just write down what I have here, you won't get full credit for it. You need to do all of them. Define the variables, rewrite it using algebra, which I have here, make your conclusion, and then rewrite it in words.
Wait, so like number...
So we're finished learning logic, but we're not finished using it. In fact, we are going to be doing proofs throughout the rest of the year, and while we're doing those proofs, we're going to be using the law of detachment and law of syllogism. Okay? So, if you're not good at it yet, you're going to get enough practice where you will be good at it. We'll be doing it in a slightly different way. We will be doing it using those proof blocks over there, and flow diagrams and 2-column proofs. So, hopefully you'll, as we work through it, you'll kind of get the hang of it. So, we are starting proofs now. This is the next topic after logic, and it naturally follows after logic because when we're writing out these proofs, we're going to be using logic. We're going to be using the law of detachment and the law of syllogism, and really more the law of, well, we're using both. So anyway, has anybody ever heard of mathematical proofs?
Oh yeah, I heard you talk about it like the beginning of the year.
Okay, I did talk about it at the beginning of the year. Will was paying attention back then. That was before he started sleeping in class, I guess. I'm just giving you trouble.
It's okay.
Does anybody remember anything that I said about proofs? No? Okay. So here's the formal definition of proof that we're going to use. And it's not really all that formal, I guess. But it's a convincing demonstration that some mathematical statement is true. And when I use the term statement here, that could actually refer to a statement or a conditional. But no, it's not in red. The purpose of most mathematical proofs is to prove that some theorem is true. So we did spend a little bit of time talking about postulates and definitions and theorems, and we'll do that again today as a refresher. But if you remember, the postulates are those things that we can't prove. Those are the things that we just assume are true. They're the most basic things. Things like between 2 points you can draw a line, and you can, given a point and a radius, you can draw a circle. Those are the things that we just assume are going to be true. The theorems are the things that we build up from those postulates. Those are the more complicated things that involve maybe multiple ideas, multiple postulates, and we put them together into bigger and better ideas, more useful ideas. We also combine it with some definitions. We have to give meaning to the words in geometry. Without a definition, we don't know what a right angle is or what a straight angle or a linear pair or any of those things are. So those things are kind of separate, and we'll get into that in a second. So anyway, proofs can be made in a variety of ways. We will do them in two main ways, but then I'll also kind of incorporate a third, just mostly showing you. We will do paragraph proofs. We won't do many of them. No, Will, can you tell Emma why we don't need to write this down?
If it's not in red, we don't need. If it's in white, we don't need to write.
I know that, but it's like.
Okay. This is just giving you some information here, just preparing you for what you're going to have to do. Of the 4 types of proofs that I'm going to show you, this is the one we're going to use the least. This is the kind of proof that you would just write out like a paragraph and say this is why something is true. It's a little bit more formal than that. It's not like a persuasive paper that you would write in English class, or they don't call it persuasive anymore, do they? Argumentative, I think, is what they call them now, isn't it? There's a difference between argumentative and persuasive. I don't know what it is, but I think they're moving toward argumentative instead of persuasive. Anyway, that doesn't matter. It's different than what you would do in an English class. It's a little bit more formal. It has to follow a sequence of causes and effects. And basically what you're doing is you're using the law of syllogism over and over again, or the law of detachment over and over again. Actually, more often it's the law of detachment. Okay? So we will do a little bit of that, but more often we'll do flow diagrams. The flow diagrams we're going to do are the proof blocks that you've kind of seen, and we'll do our first one today. We're going to do 2-column proofs. We're also going to do our first 2-column proof today. The 2-column proof is just a way of organizing what we do in a flow diagram. And then you can also prove things using technology. Now, this is a lot less formal than the other types of proofs. We can use technology to prove things because in the past, before we had computers, if you wanted to prove certain things, you would have to draw basically infinitely many pictures to prove that it's true. Now, using programs on computers, you can draw a picture that represents pretty much every case, and you can change it and see what happens when you change one part of a picture and see how the rest of it changes. You weren't able to do that before. You weren't able to draw a picture and then change part of the picture and then the rest of the picture changes for you. Okay, that's like Hogwarts stuff, and we don't actually have that. That doesn't really exist. You guys knew that, right? Hogwarts isn't real? Okay. All right, so formal mathematical proofs make use of the following to make the appropriate demonstrations. Remember, to prove something, we're trying to demonstrate that something has to be true. So we're going to use premises, and that's just the given information about a situation. We're going to use definitions, we're going to use postulates, and we're going to use theorems. And if you look down just a little bit on your paper, you're going to see we are going to talk about each one of those terms. You good, Darwin? All right. All right, so the first one is a premise. Anybody remember anything about what a premise is? This one should be the freshest of the 4 because we've talked about it most recently. You do remember? You want to share or just keep it to yourself? Okay. And there's Terrence back there raising his hand before he really thinks about it. Do you remember, Hannah?
It's like giving information that you assume.
Okay, good. So it's a given information about a situation. In this case, since we're doing mathematical proofs, it's given information about a mathematical situation. When we're proving a theorem, and we'll talk in a minute about what a theorem is, but when we're proving a theorem, the premise of the theorem becomes a hypothesis in the theorem. I'm sorry, I said that kind of weird. The premise in the situation becomes the hypothesis in the theorem. Or if you look at it the other way, if we're trying to prove a hypothesis, whatever when we're trying to prove a theorem, whatever the hypothesis is will become the premise. Yes?
Y'all right there.
Both.
Definition?
No.
What?
What's the definition?
A definition?
The meaning. The meaning.
Okay, it explains the meaning of a word, right? So the definition of a right angle tells us what the word right angle means. Actually, it's two words. So what the phrase right angle means. How in geometry class, how do we write definitions? As a biconditional, exactly. So it's a declaration written as a biconditional, which gives meaning to a mathematical term. All right, so we write them as a biconditional because we want to know what the term means. And so, for example, the definition of a right angle is it tells us when an angle is a right angle. So in this proof block right here, it tells us that it's a right angle when the angle measures 90. But it also tells us that when we know it's a right angle, we know that it measures 90. And it sounds redundant. It sounds like we're saying the same thing there, but it's really not. It's a biconditional because it works both ways. We know that when it's a right angle, it's 90 degrees, and we know that when it's 90 degrees, it's a right angle. Okay? Good definitions are always written this way. If it can't be written as a biconditional, it's not a good definition because then it's not always true. Then it doesn't always work for that term. So we like to write our definitions as biconditionals because it's more clear that way. Next term is a postulate. What's a postulate? Guys all look like you're writing something down, but there's nothing to write down yet. What is a postulate? We just talked about it, didn't we? There is a 2-point postulate, that's true. Hey, there it is right there. Good, Will. Chris, do you have it written there?
Yeah.
What did we write down before?
An unapproved and independent and indemonstrable
Good.
state.
Well done, yes.
That should be taken for granted.
Okay, you guys remember what I said? The postulates are the things that we just assume are true. You're going to say it means you can't demonstrate it. Okay? So, an unproven and indemonstrable statement that is accepted as true. So it's one of those things that we say it's true because our intuition just says it has to be true. There's no other way it could be. All right, so for example, I know you guys are writing here, but I'm going to try to keep your attention a little bit. The 2-point postulate says that if you have 2 points, you can draw a line between those 2 points. There's no way that we could prove this is always true. But is there any reason that we would think that this would ever not be true? No. What? No, a theorem, and that's different. In a science class, that would be a theory. In this class, we're going to call that, we're going to call it a postulate. Now, the difference is a theory is backed up by research and by data. And a theory at any time could be proven false if you have data that contradicts it. In this case, it's one of those things that we're just going to accept as true. Okay, so this is going to be one of our building blocks. This, along with the definitions, are going to form the base of pretty much everything we do in this class. Okay, and then the last thing here is a theorem, slightly different than a theory. It's a little bit stronger than a theory because we are using deductive reasoning to prove these theorems. So a theorem is something that has been proven to be true using postulates, definitions, and other theorems, and deductive reasoning. That should not say the deductive reasoning. Don't know why I did that. So we've defined already postulate, definition, theorem. What is deductive reasoning?
We used that earlier in the year.
Yeah, we just got done with it earlier today.
I think using patterns.
Nope, that's inductive reasoning. Deductive reasoning is what we finished up earlier today. What we just finished up earlier today. Terrence, what did we just finish up earlier today?
Nope.
No, that's what we're starting today.
What's the thing? Condition.
It has to do with conditionals.
Yeah, I know what it is, but it's like using logic.
Yeah, using the laws of logic. Okay, in our case, it's going to be using the law of detachment and the law of syllogism. So deductive reasoning is making formal arguments using the laws of logic. And in our case, the two laws of logic that we know how to use now are the law of detachment and the law of syllogism. There are many more laws and theorems in logic. These are the two that we're going to stick with. In example 10.1 here, we're given that the measure of angle A equals 90 degrees. We want to prove that angle A is a right angle. We're actually going to make this proof two different ways. I'm going to do it as a flow diagram on the board, and then we're going to put that flow diagram into a two-column format. So I'll talk about the two-column proof in just a minute, but let's look at the flow diagram here first. And so here's our flow diagram of the proof. We were given that the measure of angle A equals 90. We use the definition of a right angle to conclude that it's a right angle. So what's my first statement going to be? What did I know because of the given information?
It is a right angle.
Not that it's a right angle.
It's 90 degrees.
What was given to us is that the measure of angle A equals 90. Okay, I know that's true because it was given. Step number 2. What did I know then? What was the second thing that I knew in this proof? I first knew this, then I knew this, which is what? Angle A is a right angle. And how did I know that? What did I use to get there? What is this? It's the definition. We'll abbreviate that DEF apostrophe N of right angle. Okay, and there's one more thing we have to do. We have to show that we are done. We know that we're done because the thing that we're trying to prove, that angle A is a right angle, we have that in the column of things that we know. Guys, there's one more thing you have to write down. That means that you should probably have it out still. Since we have proven, or we have written down what we want to prove, we're going to write this. QED. That stands for quod erat demonstrandum. That is Latin for that which was to be proved. I will explain more about that mañana.